Now we're looking for this problem 418. This problem has the T-shaped cross-section and point loading applied to C, and we don't know C is the centroid of this cross-section or not. If it is not, then this is an eccentric loading problem. And in this problem, we would want to calculate the stress at point A and B, and also calculate the location of the neutral axis for this eccentric loading problem. And I will show you this eccentric loading. The solution process is this. The first, from the front view, we look at the problem, and this is the front view of the section, and the point loading applied and to here, and we want to decompose the loading problems into a superposition of a loading passing through the centroid as well as a moment about the centroid. Because this loading is not a centroid, how do we know? The calculation can be this. This is the T-shaped cross sections, and we utilize our equations. We locate the centroid, which is 3.8 inch above the, which is 3.8, that is above the bottom face. So here we locate this is a centroid. Okay, so now we put our coordinate system xy and put the origin at the centroid here. So we decompose this loading and into the combination of the axial loading and the moment, and moment basically equal to the p multiplied with the distance. And with the two loadings, we superpose into two loading conditions. One is on the axial loading, one is on the pure bending. For the axial loading problems, this is the chapter 2 topic. So the stresses can be calculated by dividing P by A. For this pure loading, the pure bending, that is a chapter 4. So here is our topic. Basically, we apply stress equal to minus my over I. And for the combination of the stresses, so basically here we calculated stress at A, which is at the bottom here. Okay, so that's a combination of the two stresses. For this one, that is minus P over A. For this case is my over I. M is the bending 24 we calculated here, and y is the distance measured from the neutral axis of this pure bending to A, which given 3.8. So that is for the stress at A. For stress at B is the same, B as the top here. That is a combination of the two loading results, which is the normal stress and the bending stress. And again, for bending stress is my over I. Y is the distance measured from the neutral axis of the pure bending to B, and that measure is 2.2. And we got the result like this. Okay, and now as far as how to calculate the locations of the neutral axis for this eccentric loading. And we remember the definition for the neutral axis is where there's a no stress or no strain. And now we look at the problem. The original problem can be decomposed into the combination of axial loading and pure bending. Here I show is the distribution of the stresses due to axial loading, which is from chapter 2. This is the distribution of the bending stress due to pure bending. So if we want to superpose the two results and looking for the location where the zero stress would occur, from here you can see that when we combine the above the x-axis both stresses are negative, so that in no way we can find a place with a zero stress. So the only region the zero stress could occur is below the x-axis, so which means somewhere here. So let me define, say that distance is E, where the location could be given to 0. So from here we see when we want to superpose the two stresses, this stress is from here and this stress is from here, and we take summation equal to 0, and that is for definition of the location of the neutral axis. So put into this equation to solve for E, and we can find E is equal to 2.411 measured from x-axis. So here is the locations. We put our origin of the coordinate systems in the position 3.8, and then we calculated E is here. So basically the neutral axis for this eccentric loading condition is basically, we can measure is 1.389 measured from the bottom side above. Thank you.